Greetings, everyone, and sorry about the interruption. We left off at this theorem that said similar matrices have the same characteristic polynomial, okay, which consequently means the same set of eigenvalues. So if you have A is similar to B, then you have B is equal to S inverse AS for some invertible S. Now, if that's the case, then B minus lambda I is equal to S inverse AS minus lambda I. Now, why do I care about lambda I being subtracted from both sides? It's because I'm going to try and find the characteristic polynomial for B, which means I take the determinant of the matrix B minus lambda I. Now, what that means is this. Being creative here, I can take lambda I, which is a diagonal matrix. It's the matrix that looks like lambda, lambda, lambda all along the diagonal with zeros in the off diagonal. Okay, so I'm going to multiply that by S inverse S lambda I. Okay, well, multiplying by S inverse S does nothing, and the line above it is equal to the line below it. Okay, but now, because I'm multiplying by an diagonal matrix, I can rewrite this product of matrices. There's a matrix, there's a matrix, there's a scalar times a matrix, into S inverse lambda I S, which means that the S inverse in front can come out. The S on the right can come out. And in the middle, what I'm left with is A minus lambda I. So at this point, you can now take determinants. So the determinant of B minus lambda I, in other words, the characteristic polynomial for B, is equal to the determinant of S inverse times the determinant of A minus lambda I times the determinant of S. Now, right here, the determinant of S inverse is the determinant of S under 1. So here, the determinant of S cancels out with the determinant of S in the denominator, and you're left with the determinant of B minus lambda I is equal to the determinant of A minus lambda I. In other words, the characteristic polynomial for B is the same as the characteristic polynomial for A. And there you go. Matrices that are similar have the same characteristic equations and thus the same set of eigenvalues. Now, the last example that we want to work through, and it's an important one, is to diagonalize, given a matrix, to diagonalize it. Okay, well, what does it mean to diagonalize the matrix? Okay, it means to find a D and an S such that D is equal to S inverse AS, where D is diagonal and S is invertible. Okay, there's something special about this diagonal matrix. It has A's eigenvalues, and S has A's eigenvectors. Now, when can you do that? This is by our theorem. This is possible when A has a complete set of eigenvectors. So for a 3 by 3 matrix, we're looking for a set of 3 linearly independent eigenvectors. Okay, so let's see what we have here. First off, we need to know what the eigenvectors are for A. Sorry, eigenvalues. So we can compute A minus lambda I, so just take 3 off the diagonal. Sorry, lambda off the diagonal. Negative 2, negative 2, negative 6, negative 3, 3, and 6. And take its determinant. So the determinant of A minus lambda I is, well, it's not easy. Let's see. There's no row or column that's obvious to expand across because there's no zeros in the matrix. So I'm going to expand across the first row. So you get 3 minus lambda I times the determinant of, cross out the row and column, minus 2 minus lambda minus 6, 6, and 10 minus lambda, minus negative 2 times the determinant of, cross out the row and column, you have negative 3 and 3, negative 6, and 10 minus lambda, plus negative 2 times the determinant of, cross out the row and column, minus 3 and 3, minus 2 minus lambda, and 6. Okay, so let's see what we get here. 3 minus lambda times, in parentheses, negative 2 minus lambda, 10 minus lambda, plus 36. Plus 2 times negative 3 times 10, so that's negative 30, plus 3y, minus a negative 18, so plus 18, minus 2 times negative 18, minus 3 times negative 2, so that's what, 6? And minus 3 times negative lambda, so that's what, 3y. All right, putting this all together, you get 3 minus lambda times, that's lambda squared, plus 2 lambda, minus 10 lambda is minus 8 lambda, minus 20 plus 36 is plus 16, plus 2 times 3 lambda minus 12, minus 2 times 3 lambda minus 12. Well, that's good. These two terms here are identical. One's positive, one's negative, so they cancel out. So we get 3 minus lambda times lambda minus 4 squared is our characteristic polynomial. And there's 2 roots. It's lambda equals 3 and lambda equals 4. Okay, this has multiplicity 2. This has multiplicity 1. So we know that there's going to be an eigenvector that comes from this. We don't know what it is just yet, but we know that there's going to be one. The only way to diagonalize this matrix is if it has a complete set of eigenvectors. So this case, we better have 2 coming from it. Okay, let's take a look. If it doesn't have 2, then I don't need to proceed any further because it won't be diagonalizable. So we plug 4 in for lambda, so we get 3 minus 4. That's what, negative 1, negative 2, negative 2, minus 3, minus 2 minus 4, that's minus 6, minus 6, minus 6, and 3, 6, and 10 minus 4 is positive 6. So these are all scalar multiples of the row 1, 2, 2. Okay, so this is 0, 0, 0, 0, 0, 0. So that means x1 is equal to minus 2x2 minus 2x3. Okay, because there's just a pivot right there. These two columns don't have pivots, so x2 is free and x3 is free. So that means the null space of this matrix is going to be the set of all linear combinations of the vectors, plural, x2 times negative 2, 1, 0, plus x3 times negative 2, 0, 1. There you go. So there's two linearly independent eigenvectors associated with it. Therefore, we're going to have a complete set of eigenvectors. Thus, this is going to be diagonalizable. So it's okay to proceed. For lambda equals 3, what do we get? 3 minus 3, that's 0. Minus 2, minus 2. Minus 3. Minus 2 minus 3, that's minus 5. Minus 6, 3, 6. 10 minus 3 is 7. All right. So let's row reduce. 0, I'm going to make this 0, 1, 1. I'm going to add row 2 and 3 together, and that's going to be my new row 2. So negative 3 plus 3, well, 3, 6, 7 is going to stay. So negative 3 plus 3 is 0. Negative 6 plus 5 is 1. Negative 6 plus 7 is 1. There we go. So that reduces. Let's make the top row 3, 6, 7. Let's make this 0, 1, 1, and that 0, 0, 0. Pivot, pivot, free variable. Okay, so let's put this in reduced row echelon form, or more or less reduced row echelon form. Multiply row 2 by 6. So 3 minus 0. Oh, sorry. One step ahead of myself. 3 minus 0 is 3. 6 minus 6 is 0. That's what I want it to be. And 7 minus 6 is 1. And that's my new row 1. 0, 1, 1, 0, 0, 0. So I know there's not a pivot in column 1 because it's a 3 and not a 1, but I don't feel like dividing by 1/3. Okay, really, we know that the null space is going to be 3x1 is equal to negative x3. X2 is going to be equal to negative x3, and x3 is free, so it's able to be itself. That's not a pivot. I'm calling it a pivot just for the sake of making things easy for me. So now I can divide by 3. So that cancels. That's negative 1/3 on that side. So the vector x1, x2, x3 is equal to negative 1/3 times negative 1 and 1, okay, times x3, or any scalar multiple of the vector negative 1/3, negative 1/3, negative 1, and 1. So I will use, I'll write this in red, I will use negative 1, negative 3, and 3 as my eigenvector that corresponds to lambda equals 3. All right. Scratch sheet of paper. Don't do that. There. There we go. Scratch sheet of paper. So, remember, diagonalize. To diagonalize this matrix, I need to write I need to find the D and S that completes this equation. So D is the eigenvalues of the matrix A. So we had what? I forgot already. 3, 4, and 4. So 3, 4, and 4. And 0 everywhere else, because it's a diagonal matrix, is equal to some mystery matrix S times the matrix A. What was the matrix A again? It was 3, -2, -2, -3, -2, -6, 3, 6, and 10. Times S. So this is D S inverse A S. These are the eigenvalues of A. These are the eigenvectors of A. And for lambda equals 3, we know that to be, let's set it right here, -1, -3, and 3. For lambda equals 4, -2, 1, and 0. And for lambda equals 4, -2, 0, and 1. And you can flip-flop these. It doesn't matter which one comes first. The last thing I need to complete this process is S inverse. So if I know S, how do I find S inverse? And the answer is row reduction. So -1, -3, 3, -2, 1, 0, -2, 0, 1, dot, 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 1, 0, 0, 0, 1, 0, 0, 0, 1. And row reduce until the identity matrix is here and S inverse will be over there. So let's do it. It's not the funnest thing in the world, but we can do it. First thing I'm going to do is I'm going to multiply by -1 on top, so I get 1, 2, 2, -1, 0, 0. I'm going to add rows 2 and rows 3 together because they both start with -3, and I can get one of them to cancel out, so that's good. If I add this -3 and 3, it gives me 0. If I add these two, it gives me 1, 1, 0, 1, 1. That's -3, 1, 0, 0, 1, 0. Okay. And the next thing I can do is I can scale row 1 and combine it with row 2. So that becomes 3, -3. So 3 plus -3 is 0. So it's 2, 2, -1, 0, 0. This is 0, 1, 1, 0, 1, 1. All right, so I'm scaling row 1 by 3. So I'm 3 times 2 is 6. 6 plus 1 is 7. Okay, and then I get 6 plus 0, that's 6. And I've got -3 plus 0. And I got 0 plus 1. And I got 0 plus 0. Right. So now, let's work on rows 2 and rows 3. So multiply row 3 by 7 and subtract. So we got 1, 2, 2, -1, 0, 0. Let's see. If I multiply row 3 by 7, I get 7 minus 7. 7 minus 7 is 0. 6 minus 7 is -1. -3 minus 0 is -3. 1 minus 7 is -6. And what? 0 minus 7 is -7. I have that, 0, 1, 1, 0, 1, 1. It's not the funnest process, but we'll continue forward. So let's make this 1, 2, 2, -1, 0, 0, 0, 1, 1, 0, 1, 1, and that's 0, 0. Change the sign on all those. 1, 3, 6, 7. Right. pivot, pivot, pivot. Perfect. There's the augmented column. Kind of stopped including that. I probably should have. Okay. Now I work my way up. I'm in row echelon form. I work my way to reduced row echelon form. So let's subtract rows 2 and rows 3. So row 3 now is fixed. It's 0, 0, 1, 3, 6, 7. I don't need to make any changes to it. Row 2 I do. So 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 3 is negative 3, 1 minus 6 is negative 5, and 1 minus 7 is negative 6. Okay, and I can change row 2 as well, or sorry, row 1 as well. 1 minus 0 is 1, 2 minus 0 is 2, 2 minus 2 times 1, that's going to be 0. Negative 1 minus 6, because what I'm doing is I'm multiplying row 3 by 2. So minus 1 minus 6 is minus 7. Okay, I get 0 minus 6 times 2, that's negative 12, and that's 0 minus negative 14. All right, so there's a 0 above, zeros above this pivot. Now I need zeros above this pivot. So I need to multiply row 2 by 2 and subtract. So 0, 1, 0, 0, 0, 1, negative 3, negative 5, negative 6, and 3, 6, and 7. All right. So we're multiplying row 2 by 2. 1 minus 0 is 1. 2 minus 2 is 0. 0 minus 0 is 0. Negative 7 minus a negative 6. That's negative 1. Negative 12 minus a negative 10. That's negative 2. Negative 14 minus a negative 12. That is another negative 2. Lo and behold, we are done. There's the identity matrix. That's S inverse. So, putting in the last group of numbers, the inverse to S, S being the eigenvectors of A, is negative 1, negative 3, and 3. Negative 2, negative 5, and 6. And negative 2, negative 6, and 7. Okay. And that's how you diagonalize the matrix. Okay, just as an aside, real quick, I'll go to this set of notes. What we've demonstrated, that since A is diagonalizable, it can be written as D equals S inverse AS. And you can confirm that, okay? So if I had the time and the patience, I can multiply A and S together and then multiply the product of that with S inverse and get this diagonal matrix over there. But what you can also do is multiply both sides by S and both sides by S inverse. If you do that, you get the equation SD S inverse is equal to A. So sometimes students choose to say, hey, this matrix A is equal to SD S inverse, where S is the eigenvectors of A, S inverse is the inverse of that, and D is the diagonal matrix with A's eigenvalues. And that's okay too. Okay. But there you go. That's how you diagonalize a matrix. You don't know this yet, but this is incredibly important for the word problems that we are going to do after the next midterm. Okay, so being able to diagonalize a matrix is a very important the word's escaping me right now, but it's a very important technique that you want to master for future success. Okay, and so make sure you do it. Make sure you can do it. All right, that's the end of the content I want to lecture on from 7.3. I hope you're having a good evening.